Hello. Good morning, good afternoon, good evening, whenever you've been watching this video. Welcome to another IB lesson from me. And today we're going to be taking a look at IB diffraction and interference, which is covered in topic 9, specifically topic 9, 9.1 and 9.2. If you had taken the course with me, most likely 9.1 is already covered in the physics 20 level along with diffraction. However, I will still go over the fundamentals of 9.1, which is single slit diffraction. Okay, but our focus is actually on the multi-slit diffraction, which is covered in topic 9.2. This is the last exam for the year of 2024, and the topic is still covered in the new IB curriculum. It's just under a different section, right? So without further ado, let's get started. So for those who know that once you have once you have a wave that passes through a opening, it will diffract around the opening and form a pattern per Huygens principle. Okay, if we treat each point on the wavefront as a separate wavefront, okay, then we can actually explain why, or at least behaves like wavefront. I'm gonna send this image over. Oops, something wrong with the mouse here. There we go. This is Johannes Huygens. Okay, Christian Huygens. Okay, if you treat each point on a wavefront, then you can explain why the wave diffracts. Okay, so what the wave diffracts, of course, will correspond to something like this. All right, and which is that each point along the wavefront acts as a point source. And that point source, spoilers for what's coming up. Okay, each point source will simply bend around the corner. Okay, because the normally in the middle the wavefronts left and right got cancelled out, the forces cancel out. So that's why you do not see the circles. In circular nature, you only see a constant horizontal wavefront because there's interaction between these source and this source. Basically cancel each other out. However, on the edge, there's nothing to cancel the wave from this side off, so that the circular wave is free to bend out. Same thing on this side, so that's why you see the bending of the wave. And you'll notice that if the smaller the opening, right, means less wave points get through, which means there's going to be more bending. So first wave is very flat. Okay, while last one was really small opening, it's a really circular wave. However, there is a problem. If we do treat each point as that's a separate, well, it's not really a problem, but a prediction, okay? Which is if we do treat, okay, you didn't move with it. Okay, if we do treat that each point on along the wavefront as a point source, then those waves will of course interfere. For instance, when you get sufficiently far enough, right? Like the top picture, you notice this wave right here, right? This wave right here from this source is going to interfere with this wave right here, which is from a different source. I think that one looks like from this source. So that point and that point is going to interfere, which means it will form an interference pattern. Okay, interference pattern, constructively or destructively. All right. So when the wave, if we put the screen on the very far end right here, the wave will not arrive as a uniform. Wave. Okay, if the path difference, right? If two waves, right? If two waves are completely overlapping each other, if the path difference, right? Let's say this wave, they all start from the same spot, right? But this wave travel a bit shorter distance. This one travel a little further distance, right? This would be the path difference. Okay, path difference. Now they both end on a minimum, right? Both minimum, and then it's end up on a minimum again. So the path difference here is exactly one wavelength. You'll notice as long as the path difference is exactly a whole wavelength, the wave will always line up perfectly, which means they'll have constructive interference. So for the path difference, let's call it delta L. This is called the path difference. Okay, if that's exactly an integer times a wavelength apart, it will be construct interference. On the other hand, this is the minimum, maximum, like usual. However, if we have exactly a maximum, then minimum, then maximum, then minimum, then maximum at the mark, and that's what's going on, right? You'll notice that the minimum, if we match the minimum to the minimum, right? The minimum is right here. To this minimum, exactly, it's from one maximum to one minimum. This is exactly half a wavelength. So the path difference is exactly half a wavelength, right? If delta L is about, well, not exactly half, but whole number plus a half, right? Just a little bit off. So I'm plus 0.5 of wavelengths off. All right. Then we say that this is going to be a destructive interference. Not to say, but it will happen, right? Because the peak and the trough is going to cancel each other out. All right. The coefficient right here, we call it the order number. That's the order. Why do we call the order? You see, if this wave, for instance, this wave, we're allowed to propagate to like a screen over here, right? It's going to land, okay, it's rotate sideways so that the diffraction passes through a wave, and then along the middle, it's going to be all constructive, and then it's going to be all destructive, then constructive. So it's going to form a pattern very much like the one you see right here. In the middle, it's going to be constructive. Here's going to be constructive, but here's going to be constructive. Here's going to be constructive. But in the middle between them, it's going to be destructive. We describe the order, okay? The order of those antinodes, which call these constructive is called antinode. Node. This is called a node. The constructive antinodes, we give them order number in the middle. We call it order 0 because it's directly in the middle. So all the wave travel about the same distance to the center. So there's no path difference. The second one, right, is a little bit off. So the one in the middle is going to travel further than the one from the side, as seen in the picture here, right, to this point. So this one, the path difference is going to be exactly one wavelength, and the next one is going to be exactly two wavelengths. That's the order. And in between, this one will be 0.5. 1.5. That's the order number. Maybe I should not use the letter N here because N is confusing. Maybe we should use something like K. However, on the IP formula sheet, they use the letter N here. But also N for order numbers. Okay, of order numbers. All right. So that is what we expect to see if lights a wave and diffracts according to what Huygens has described. Christian Huygens has described. At each point is diffraction. And when an experiment is done, that's exactly what happens. Okay, that's exactly what happens. Just say it looks something like, one quick second. Okay, something like, I'm going to spoil the next page. Something like the top right here. Okay, the bottom we'll talk about later. Okay, top right here. One big blob in the middle, some smaller blob on the side. Exactly. Like what is that? What they described? I should use different color. There we go. Describe one small blob, blobs. That's exactly what happens. However, it is very, very dim. Okay. However, it's very, very dim. Okay. We'll talk about intensity a little bit later. Okay. But that's what actually happens. Now, not only that, Huygens has able to use some simple trigonometry. Okay, to calculate exactly how much deviation it expects to be because. Using this our understanding. So the calculation is now to the first minimum right here. Okay, to the first minimum right here. Let me change this in pen here. First minimum right here. The minimum is destructive interference, which means the path difference should be 0.5 of a wavelength apart for the closest one. Okay, so assuming right? The opening, usually the way it's very small. The opening is going to be very, very small, few millimeters, if not smaller apart, while screen is going to be meters away. So assuming the opening, we call the slit opening, which we call B, and distance from the slit to the screen, which we call L. If we assume that the value of B is much smaller than distance to L, like millimeters or smaller compared to meters, right? Very, 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 very big difference. Then we can use some simple assumptions here. All right, simple assumptions. Okay, which is that if we draw a right angle to calculate the path difference right here, okay, right angle right here. If we assume that's the case, then okay, the angle it bends right here. Okay, angle it bends right here. So if we draw a central node and measure the angle from the center to the first minimum, that angle right there, which is labeled right here in the picture, that angle, okay, is going to be approximately equal to this angle right here. Okay, because these two beams are effectively parallel. Okay, like for a very long distance. So you can, it's a little bit tricky to show that, but they're very close to each other. Okay, very close to each other. All right, now the red path on top is closer and blue path on bottom is further, so this is going to be travel further. So this tiny distance right here is our path difference. Okay, path difference. All right, now since that path difference is exactly to the first minimum, so we know the first minimum, right? The path difference should be exactly half a wavelength apart. Okay. However, the path difference can be related to the angle and half the sides of the hypotenuse over here. But the hypotenuse is exactly half of the slit opening. So delta L is also equal to sine theta, right? Sine theta, right? I should probably be a little bit more specific. Okay. Opposite over. Oh, maybe I should write it down like this, so I don't confuse myself. All right, which is that sine of the angle is equal to opposite over adjacent, which is 0.5 divided by 0.5b, which you get lambda over b. All right, so we got the formula. Sine theta is equal to lambda over b. Okay, so using the Huygens relationship, we can actually say that sine of the angle of diffraction to the first minimum, right, is going to equal to lambda over b. However, if we use radian, and for those who are fluent in calculus, they will know that limit as theta goes to 0 of sine theta over theta goes to 1 is equal to 1, which means sine theta and theta and the angle itself is very close to each other in radian. Okay, and because we made the assumption that b is very, very small compared to this screen distance, so the angle is going to be much smaller, usually less than 10 degrees. Okay, when that's the case, we can make a reasonable assumption, the estimation I should say, that sine theta is approximately equal to theta. So we get the formula that's actually on your formula sheet for IB, which is the angle measured in radian, remember, is approximately equal to lambda over b, which means the angle of diffraction for a single slit is approximately equal to the wavelengths of the light passing through the slit over b. Okay, over b. All right. Just note that the actual formula is this. Okay, we're using a small angle approximation. All right, and the angle is the angle to the first minimum. Okay, angle to the first minimum. All right, turns out for the first few orders, the angles are very similar, close to each other. So so it's actually angle between the minimum as well. So first minimum it will be lambda over b. Second minimum will be 2 lambda over b, and so on for the first few, with the angles still remain fairly small. Okay, angles still remain fairly small. So there is a formula for single slit diffraction. That's how much diffraction happened. Alright, nice and big. And this is the angle to first minimum. Okay. And this formula is for single slit diffraction. Now, this is just an estimation, but even with this estimation, this can give us a lot of insight on what we expect to see when we change, as you can see at the bottom of the screen here, what we expect to see at the when we adjust the values of the wavelengths and the slit opening. For instance, okay, let's say on the very left, right here, is what it looks like through a diffraction. Okay, one particular slit. Okay, first of all, intensity in the middle, the central node is super bright, as you may remember from the picture I showed you, really bright. The next one's really dim. Okay, in fact, it's about 1/20th of the intensity, while the next one's about 1/50th of the intensity, and so on. It gets really dim really fast. Okay, now if we look at the angle of diffraction, the first few will follow what we expect of the rules, provided once again the screen's really far away and the angle is very small. So this one is about where lambda over b, as we figured out the first minimum. Second minimum will approximately where lambda 2 over b, 2 lambda over b, double the distance. Third minimum will be approximately where that location, okay, from the middle. Remember, it's an angle, measurement angle from the middle, right? From the middle, the angle will be that far away, okay, for the first few minimums, all right? That's what's going to happen. Now, what happened if we change the opening? Well, as we know, right, the angle is inverse proportional to the opening, which means if the opening goes down, the angle will increase, right? So become wider. Of course, you also let less light through, so intensity first will decrease because you have less light going through, because your hole is smaller, right? So it will become wider. So which means wider. On the other hand, of course, if opening becomes narrower, if opening becomes wider, the diffraction has to become narrower. Okay, become narrower. So the whole thing becomes wider. I can see in the purple one. So remember the red one is the original one, and the purple one I got the color backwards here. Okay, so it become half the width. It's going to spread out more. Further, okay, if I change the wavelengths, if I change the frequency, really, change the color of the light, right? Change the color of the light. Then remember that the angle is proportional to the wavelength, which means if you have longer wavelengths, the angle is going to be more, which means if you have a big wavelengths, like red, long wavelengths, you'll diffract more. And something like purple or blue, it's going to diffract less, which as you can see here. So red is the widest on top here, and then green, and then purple is narrowest. And this is why if you have a white light, which is made up of different colors, a single slit can actually, it's hard to see, of course, because the wavelength is very small, right? Very small. So even if you multiply by 5, it's not going to be noticeable until really far out. But if you use a white light, you can actually form something like if you superimpose them together, for instance, right? If you superimpose them together, right, you get, so this is 3 different colors. You will get something that is very similar to, down a little bit. So you see, well, I don't know why it's not copying over my picture. There we go. Something like that. All right. When you combine them, right? If you combine them, right? So you'll notice red bend the most, Red on the outside, purple on the inside. So it's actually repeating, right? Red on the outside, purple on the inside. So this is one of them. So this is one set color, and there's another band, and so on. Okay, another band right here, one band here, one band here. So there's 3 bands right here. Other one, red to purple, red to purple. Okay, so you get the 3 diffraction as before. Now this one's of course greatly exaggerated. The effect is greatly exaggerated here. Okay, greatly exaggerated here, but that's what's going to happen. And then if you squint, that's sometimes you can. If you squint really tight, actually, with your eyes, looking at really, really bright light, sometimes you may see the effect when the light gets really out. Because, like I said, in the middle, the spread is not going to be very. It's going to be very close, and the spread, the effect is going to be more significant when it gets further out as the angle is spread out. The difference between the angles become more significant. Right, and that is a single slit diffraction and interference. All right, of course that's all interesting and all, but that's not the whole. That is not the whole picture. Okay, that is not the whole picture. But now it's a good time if this video getting long. It's a good time to take a little break before you jump into this next section of this lesson, which is 9.2. All right, on comes topic 9.2. 9.2, okay, 9.2 is about multi-slit diffraction, specifically double slit. Okay, double slit and more. Okay, double slit and more. And double slit is something you're probably fairly familiar with, so I'll not spend too much time going over. Veritasium has a wonderful video going over it, so I'll direct you to watch the double slit experiment, the details of that over there. But in keep short, what happened is the wave from each slit. Okay, so it's more obvious. It's going to form a circular wave of their own, and no circular wave interfere, and form a pattern that looks like that. Okay, it looks like that. However, it's very important to note. That each slit from earlier, from 9.1, each slit has their own diffraction already, right? That's not going to go away. So each of the slit will first produce a. I'll change the color. Will produce each slit will produce a pattern that looks like this from earlier. A double slit will do their own interference, but that interference will be affected by the brightness and caused by the single slit interference. So double slit got forced inside a single slit one, like so, as you see on the bottom. This is what Young observed, and this is Young's double slit experiment. Thomas Young's double slit, very famous experiment that demonstrated light is a wave. Now, only a wave can do that. As we described earlier, we use the property of wavelengths, and so on. So only a wave can do that, which is usually credited for a definitive proof that light is a wave. All right. So of course, we still have the same assumption, except this time the distance between the slit, we don't use b. Okay, this b is the width of the slit. The distance between the slit, we use the letter d. D is the distance between the slits. And of course, we still make the assumption that is much smaller than L. And for Thomas Young's purposes, okay, the angle is also very, very small, the angle of diffraction between these two. Remember, this two is already less than very, very small. This one must be even smaller, right? So that's going to be definitely less than 10 degrees, so small angles. Okay, small angles. From there, Thomas Young was able to drive the formula. If you're in the Alberta curriculum, you know the formula very well. The formula is the wavelength is equal to dx over nl, and n of course is the order, n equal to 0, n equal to 1, n equal to 2, and so on. Alright, that's a famous Thomas Young formula. However, unlike Young didn't really care about all the other nodes. You only really care about the central and the first order one. You only care about n equal to 1. Alright, n equal to 1. And Young also, and the notation associated with it is also a little bit different. Okay, a little bit different. So, the formula, I'm just making sure, I get the formula for Young's notation. Okay, for Young, okay, instead of a distance L, he used symbol D, right? And the separation, instead of X, he used S. So Thomas Young have the formula, looks something more like this, ds over d. And he rearranged it because he's manipulating, right? He's manipulating the wavelength and trying to see and how that affects the separation between the slits. So by rearranging it, he was able to get S is equal to lambda d over d. So that is the formula on your IB formula sheet. Just remember, S is X, this is IB. This is operator curriculum. S is X, and D is L, and N is 1 is N. Okay, we assume we only care about the first order maximum. Okay, first order maximums. Okay. All right, and once again, you may notice that these fringes, right? These bright spots are approximately about the same distance apart. Later, it's harder to tell. Okay, in fact, it actually becomes more significant as angle get bigger. But just like Huygens principle from earlier, single slit diffraction, okay, Thomas Young noticed for the first few, usually in the middle, the first few for one n is very small. First few n very small, right? First few n's usually like first about 10. Okay, that's usually will not be given a number. Okay. He says that the width is it's about the same. Okay, it's about the same. So he also draw the reasonable conclusion to estimate that the distance between all the maximum, the distance between all the maximum. So this distance, of course, here is S, right? That's S. But this distance here is also S. This distance here is also S, which means you can find a distance between the fringes, the bright spots. Okay, they are all equal to lambda d over d, lambda d over d. So this distance here will be, this distance of course is lambda d over d. That's the definition, right? The first one. But this one is also lambda d over, there's 2. So the total is 2 lambda d over d, and so on for the first few. Okay, for the first few nodes. He didn't really care about what's too far out away, it's harder to measure. Okay, he didn't really care, but for the first few, okay, you will notice that they indeed work like that. Okay, so this is not actually the formula for the distance to the first maximum, but this is actually distance between the maximums. So the S is actually distance between the principal. I'll say the word principal here for a reason. You'll see why in the next slide. Max. Okay, principal max. And why is it observed this way? Well, what happened is, of course, when you have single slit diffraction, you have the single slit diffraction pattern on the left over here. Okay, on the left over here. And remember, that is what happens when each light from each bulb have to have that. The light will land on there in following this pattern. However, there's a double slit experiment, the double slit interference over there. Double slit interference will not override a single slit one, right? We have to follow a single slit. So double slit got sort of enveloped, right? It's got enveloped, okay, enveloped by the single slit, right? Because you have to have single slit one first, and a double slit sort of falls into it. Right? So you'll notice that because of that, unlike the maximum, like single slit, the maximum in the middle is really bright, the next one is super dim. Now, the central bright spots are really bright. The next two are also really bright because they're both still in the bright one in the middle. And, of course, for Thomas Young, he really only cared about these ones. The other one didn't really care about as much. Okay, and those falls in a small angle, so you can use this and say the distance between them is approximately equal, and then all lambda over d, lambda d over d. All right. Now, of course, eventually we will care about the ones on the side, but those will be talked about a bit later. All right. So that's what's happening for double slit experiment. Not only is the formula and why double slit look like these blobs is in blobs. Okay, and that's what's happening, and that is because, okay, of this enveloping effect from a single slit interference. So here come some questions. Simple question, for instance. Okay, I'll write the formula down over here. S is equal to lambda D over D. All right. So what happens if I double the slit interference pattern when a slit width is increased, but a slit separation remains the same, which means I increase the B, right? That's the slit opening, slit width, but D stay the same. Now remember, D is what governs how far apart these things are, these maximums are, right? So that distance separation won't change. So if I draw it out, let's say trial number 1, right? If we draw it out, here's the middle. Then if you have your single slit interference pattern, right? You have a single slit interference pattern. Let's draw it in blue. Okay, so a single slit is like maybe something like that. We'll have to change the thickness again. And now your double slit one is enveloped inside, right? So you'll notice this here actually have a bump and a flat and a bump, so you actually have a flat area here. Okay, something like that, right? So let's see for the first trial. Now I double the B. Now remember, when I double the B, B only affects the interference pattern of the single slit, because remember the angle is approximately equal to lambda over B, and when B doubles, right? Because inverse proportional, when B doubles, the angle of diffraction halves, which means the single slit one will become narrower. The single slit become narrow, sort of like that. It will be like, see, narrower. However, the number of separation for a double slit did not change. You still, let's say in the first one, there's still 1, 2, 3, 4, 5 fit in the central node, central block. There still needs to be 5 fit in there, right? It still needs to have fit 5 in there because that distance didn't change, right? So you have still 5. So the only way for that to work, all right, is to have them become narrower, okay? Become narrower. So modulating maximums will have to become narrower, okay? So, and that's what happens. Oops. That's what happens. It's so it was increased, okay, because the separation is constant, right? Everything else is constant. So that means that the modulating maximum must become narrower. Okay, must become narrower in order to still fit in that distance. And fewer, yes, and of course you'll also be fewer because you can fit less in there, right? The next question, of course, is something like this one. Okay, so double slit. It's a graph shows the intensity of the light, some unit, doesn't matter. Some diffraction pattern produced below, and the wavelength of the light is 510 nanometers. Okay, nanometers. What is the slit width, and what separation of slits? Okay. I'm not going to go through this question in too much great detail, but in general, when talking about slit width, this one you should be using single slit diffraction formula. Right, you're working with a single slit. It's affected by the single slit, so this one is about angle approximately to lambda over B, right? And the angle to the first minimum. This is the first minimum for the single slit, which means it's right here. Just remember, here is kind of the weird one, which like it's supposed to be another one, but you'll be blocked out, and then like that. That's where the minimum happens. Here's the minimum, because here's going to be a node, and the second one will be cancelled out, and then you have another one over here on the other side. So that's where it looks weird. Okay, you will have a weird wave here. So you will use this distance to the middle. So the angle is 0.1 radian, so 0.1 is equal to wavelength, so it's 510 times 10 to the negative 9 meters over B. So B is equal to 510 times 10 to the negative 9 meters over 0.1, which is going to be, so basically you may notice that it's divided by 0.1 times 10, right? So it's 500 times 10 to the negative 9 meters, okay, which is so it's 5,100 nanometers. Right? A little bit bigger. As for separation of the slits, that's about a double slit. So this one you should be using the S equal to lambda D over D, and you're looking for D here. I'm going to rearrange the formula here first. So D is equal to lambda D over S. However, you say, but I don't have D and I don't have S. I only have the angles. How do I do that? Well, you see, if here's a screen, here is a central node. Here's a screen right here, central node, and here is let's say this is the first order, second, 3, 4, 5, 6, 7, 8, 9, 10. Tenths. N equal 10. Okay. 10th order. So I guess you don't really have to do that, right? Let's say N equal to 1 because, okay. Let's see N equal to 1 because that's where the formula comes from. N equal to 1 because that's where the formula comes from. To take the distance divided by 1, so 0.1. So this distance will be just exactly 10 of them. This distance will be 0.01 radians, right? At that distance. So we know S is actually equal to, I shouldn't say the S. So we know the angle over there is exactly equal to 0.01. How is that helpful? That's because, right, if we take the tangent of the angle, right, tangent is opposite over adjacent, which means tangent of the angle is actually equal to S over D. So D over S is just 1 over tangent of zeta, or those who like cotangent of the angle. Cotangent of the angle. So this is just lambda over tangent of the angle, which is lambda over tangent of 0.01 radians, whatever that is equal to, which I cannot do it in my head. All right. So that's it. Okay. All right. So you can do that as well. And there is double slit interference. Okay, that's part of 9.2. Right. And okay. Now it turns out this is not part of the IB formula sheet, so it's not something you need to know, but I think it's fun. But it turns out that intensity of the central maximum happens to be exactly n squared, number of slits shined, squared times intensity of the single slit central maximum. Okay, so and the central maximum for n slits is going to be In times that. So the central actually becomes much brighter. Okay, actually become much brighter than the one in the middle. Okay, than the one in the middle for a single slit because it's so narrow. Okay, so it's easy to be identified. All right. And now, if you have another time to take a good break, if you want, you can pause this video, take a break before you come back for section 3. Oh, so welcome back, or you didn't pause, continuing. So your question might be, what happened? So we have a single slit, we have double slit, what if we have 3 slits, 4 slits, 5? Well, very good question, and those has been, of course, being asked as well. So what happened is, this is more qualitative, okay, than quantitative, okay, but what happened actually is that, remember the enveloping effect? That's still happening, as you can see here on the left over here. Okay, the enveloping effect is still happening. However, what happened is you can fit the beams become narrow, the interference pattern become narrower and narrower. Okay, narrow and narrower. So central, the location. Okay, we can talk about location in a bit. You become narrower and narrower. Suddenly, when you get to 3 slits, you start introducing these second order maxima right here, 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 here. And then when you get a third order, there will be 2 second order maxima instead of principal or primary maxima. So that's why I call it primary maxima. Okay, you start having 3. 5 is really hard to see. It's actually 3. 1, 2, 3. 1, 2, they're hard to see, but it's right there. Okay, 3. So there's always going to be, n minus 2, right? Let's say, okay, I shouldn't say, n is used a lot already. So the number of this capital N, the number, let's use green for multi-slit, different colors. Single slit is blue, double slit is red, single slit is green. So number of secondary is always equal to number of slits minus 2. Okay, minus 2. So if 2 minus 2 is 0, 1, there's not even like the primary maxima you see in the big blobs, right? The second double slit. So what you see is that the primary or the principal maxima gets narrow and narrower, Okay, it's still enveloped in the single slit effect, right? Become narrower, which means it's become more and more clear. Okay, and introduce a number of secondary ones, like these. Okay, you'll notice no matter how many slits you add, where the central maximum is always lined up. The principal maximum. The central one is always the same place. The second principal maximum, same place. You just fill it with more secondary maxima. So location of the principal maxima is always going to be the same. Okay, it just become more and more defined. Okay, however, that is assuming you're just adding more slits sideways. Okay, So what actually happened for diffraction grading is instead of just adding more slits, they're trying to fit more slits in the same area. So instead of you're adding more slits like this, you have a set width, and you're trying to fit as many slits here as possible, which means you're actually making the slits narrower. So when slits narrower and closer together, and if you remember the formula, if the slits are narrow and closer together, the diffraction becomes wider. As well. And as a consequence, when you have something like thousands of slits per millimeter, okay, like a diffraction grating, okay, the angle no longer works. The angle becomes too big. The angle between the maximum becomes too big because you're trying to fit all the slits in there, right? You're trying really, really small slits and lots of them really close together. So diffraction, suddenly the angle becomes too big. When that happens, neither the formula we learned earlier will suffice because they'll assume the angle is less than 10 degrees or very small. So what happens if the angle is too big? That's when you use good old trigonometry, and we don't assume sine theta is equal to theta. We just say sine theta is sine theta, and we get the formula that you're nice and happy familiar with from the Alberta curriculum, which is lambda is equal to d sine theta over the order. Okay, over the order. Now, especially when we're not looking at the first order anymore, we're looking at the second order or third order, the fourth order maximum. Okay, fourth order maximum. Remember, this is only for the principal or the primary. I think on this slide says primary or principal maxima. Okay, not secondary ones. This formula only works for that. IB, we arrange the formula. It's equal to d sine theta. This is more intuitive because n lambda is just a number. D sine theta happened to, if you remember correctly, d sine theta is just equal to the path difference. The path difference exactly a multiple of wavelength. Makes sense, right? So that's the formula on IB. It's the same formula essentially, right? Essential formula, and this works for any order. and any angle. All right, any angle. Now note, a question can be asked is, what's the maximum number that can fit in? Just remember the maximum angle of diffraction. You cannot diffract more than 90 degrees because 90 degrees go backwards. You can't see anymore. So Mx is always going to be less than 90 degrees. You can never equal 90 degrees because going sideways, but we usually use 90 degrees as a maximum possible diffraction angle. Okay, maximum diffraction angle. And that's the formula we use for anything more than 2 slits. Anything more than 2 slits, like diffraction, diffraction gratings. Okay, diffraction gratings. Now, I know I moved things around. I wrote notes in the middle of a question, but I moved the question down. There we go. So a question could be asked then. All right, here's the interference pattern. How many slits are in diffraction grating? That's very easy because we can count the number of secondary maxima, which is 1, 2, 3, 4, 5, 6. So number of secondary is equal to 6. That means the number of slits is 6 plus 2, which is 8. A more interesting question. Okay, I'll move this one later. Try this one. Ooh. I'll move this down a little bit. All right. A more interesting question would be something like this. The separation between principal maximum is 0.2 centimeters. One red light is shown upon it. Okay. What is the separation of the same light? Okay, wavelength does not change. Shine upon it. Grating was double the number of slits, but the slit separation is unchanged. Right? So separation is unchanged. And let's see here. What's the separation like? I want to show with double the number of slits. Okay, but assume the slit separation is unchanged. Separation unchanged means D is unchanged. Right? D is unchanged. Okay. The separation of principal maxima. Okay, yeah. So these principal maxima is 0.2 centimeters, which means so if we draw a picture here, right? Let's say n equal to 1, just keep things simple. Okay. That distance didn't change. That distance is 0.2 centimeters. All right. So that 0.2 centimeters. Now the sign of the angle wouldn't change, right? Because you're shining more. Oh wait, but the slit separation didn't change. As long as slit separation does not change, you can shine even more number of slits. You will not change the effect of the. You will not change the slit separation. You will not change the. You will not change the separation of the diffraction, the principal maximum at all, right? Because the principal maximum is always at the same spot. What will happen instead is now, since you have double the number of slits, right, you'll have, well, correspondingly about double the amount of secondary maxima. So what's going to happen, okay, what's going to happen is they'll become narrower, okay, they'll become narrower and clearer to identify, but they will not change their distance, as we indicated here. As long as they keep the same number, as long as they keep the same slit width, you will not change the location. There's no change. No change. Okay. There's no change. That's what I'm seeing here, right? If you increase the number of slits, you will not change the separation of that, as long as the separation does not change. Okay. However, what actually happens in practice, of course, is the other way around. In order to increase the number of slits, we have to halve the slit. We have to halve the slit separation, which means it actually becomes further apart. It actually ends up being further apart because it's inverse proportional. It ends up being further apart. So the angle becomes bigger. Sine of the angle becomes bigger. Right? All right. Last but not least, okay, something like this. Orange light with wavelength 590 nanometers. Shown upon diffraction grating, what's the maximum number of slit per millimeter produced 19 principal maximum on the screen? Which means maximum one is, it says 19 principal maximums. Be careful, it's symmetrical. It's symmetrical, right? Which means 19 would be 1 central and 9 over here and 9 over here. Okay, so the order number is actually equals to 9. Now, what's the maximum number of slits per millimeter? That's talking about, well, slit width, right? If we know a slit separation, let's say, which means it's a D. Because if we know the slit separation, we can just say, oh, slit separation is 5 millimeters, for instance, right? Then 5 millimeters, then, well, okay, let's say that. 5 nanometers, then how many 5 nanometers, so how many 5 nanometers can fit into 1 millimeter? So we're actually looking for D, because the number of slits per millimeter is just equal to 1 over D, because if we flip it around, it becomes millimeters per slit, right? 1 over D. All right. Now it's just be careful. The units we calculate is in millimeters. Okay, so we want to make sure we convert the units properly to the corresponding units. Okay, because this is 10 to the negative 3, right? 10 to the negative 3 meters. So convert once again, just convert to the correct unit, right? So D, of course, we're looking for D, and then let's see what we know. We know the wavelength is 590 nanometers. Okay, and you say, well, if only we have sine theta. However, it's asking the maximum number allowed to have 19 maximum. Maximum was maximum number, which means to fit as much as possible, right? Because if you become narrower, right? If you're narrower, you can fit more, right? So if you fit more slits in there, you can fit more. So that means you have exactly 19, which means the largest possible distance is 19, right? Largest distance is 19, which means the angle is actually equal to 90 degrees because it ends exactly where it is. It's as wide as it can be, right? As wide as it can be. Remember, wider, I mean, hold on. Maximum number of slits per millimeter, because you have more. Oh yeah, because if you have more, they will become wider. You can't fit 19 anymore, right? Because you become narrower, you become wider, right? So you have to be as wide as can be, which means as wide as can be, right? So if you become narrower, if the slits become even smaller, even closer, the slit has to become closer together, which means the diffraction will be wider, which means you won't fit 19 anymore. So it's maximum possible, which means you have the widest possible separation, which means you achieve 19 around 90 degrees. So that's what's actually happening, right? Because this is maximum possible, widest possible. Why? My computer is stuck. Widest possible is 90. And from there, you can easily calculate the value. Okay, from there, you can easily calculate the value. Oh, there we go, it's working again. So we use the same formula, n lambda equal to d sine theta. We're looking for d, so d is equal to n lambda over sine theta. Theta is 90 degrees, or pi halves if you want. So this is equal to 1, which means this is exactly n, of course. N is equal to 9 times the wavelengths times 10 to the negative 6 millimeters. Okay, you multiply that out. Okay. So, multiply that out. And the calculator here quickly. So multiply that out. It's 9 times 590 nanometers. 9 times 590 nanometers. So that will give me a value of 0.00531 millimeters. All right. And then I just need to take the reciprocal of that. So that's how many millimeters between every two slits. So we'll take 1 millimeter divided by that, right? 1 millimeter, so we'll take how many slits. So we take 1 millimeter divided by that, we get, so that means this is the same as exactly, oh, I think I made a mistake here. So we get a 88.3, but that didn't work, right? Because the large number is 1. You cannot go 180. So it's 1. The answer is 188.3. But that the number doesn't work because you cannot have 0.3 of a slit. Now, be careful now. If you have 180, so should it be 189 or 188? Just remember, if you have more, that means the slit has to be closer together, which means the diffraction will have to be wider, which means it cannot, even 100, it's 188.9, even that's the value, it cannot be bigger than that. Okay, it cannot be bigger because if it's bigger, this diffraction becomes wider, which means you can no longer fit 19 inside 90 degrees, right? It cannot be wider. So you always round down, always, okay? Because it's maximum numbers, so you cannot go beyond that. So it should be 188 slits. So the answer is 188 slits. So wait, 1 millimeter, I should write it down, divided by 0.053. 1 millimeters is equal to that. So there we go. So that's maximum number possible, because if you go 189, it's bigger than the 188.3 figure. So you cannot fit 19 principal maximum on the screen anymore because the diffraction now is too wide. Okay, it's too wide. And that is single, double, and then multi-slit diffraction of light. Thank you very much for watching, and I will see you next time.